MonB5G is an acronym for the H2020 5GPP ICT20 project titled Distributed Management of Network Slices in Beyond 5G. It provides a zero-touch management and orchestration platform to support large-scale network slicing and automatically manage the underlying communication networks without human intervention for 5G and beyond. The MonB5G system emphasizes security and energy efficiency, providing a distributed and scalable architecture for next-generation networks. A data-driven system relying on artificial intelligence techniques is deployed to distribute management and operational tasks throughout the network. Because of its design, it can adapt to changing conditions in real time and use artificial intelligence-based techniques to detect and mitigate attacks on the network to improve security and reduce reaction time thanks to a local decision-making process. In summary, the MonB5G system will enable network operators and service providers to offer a wider range of high-quality services to their users with a focus on adapting to new needs and delivering high-quality experiences.
MonB5G demo architecture consists of two layers: management and orchestration layer and the infrastructure layer. In the management and orchestration layer, we have domain management orchestrator and inter-domain management orchestrator. MonB5G infrastructure layer consists of three domains: radio access network, core network, and application domain. MonB5G monitoring system aims to gather detailed information on network slices deployed across multiple domains. All system components are implemented as containers, including the sampling functions, and deployed as pods in a cloud-native manner. Federated learning and anomaly detection proof of concept involves 3 sites, each with a Kubernetes cluster running a monitoring system instance.
The first proof of concept leverages highly distributed MonB5G mechanisms, namely monitoring system, analytical engine, decision engine, and actuator, to enable automated zero-touch service management across domains. This proof of concept enables network operators and service providers to avoid network service failures, reduce network resource management time and overhead, and ensure that their end-to-end cross-domain service level agreements are met. In the first proof of concept of MonB5G, we have 2 scenarios. The first scenario evaluates data-driven network management system in a multi-domain system. The first scenario consists of 2 demos. The first demo is based on a federated learning approach to reduce network overhead, energy, and improve performance prediction for network slices. The second demo relies on LSTM-based and graph-based interpretable anomaly detection techniques to reduce reaction time to network slice malfunctions and improve the accuracy of slice performance degradation detection.
A user device connects to a G Node B that provides access to a virtual reality streaming server, which is deployed as an Nginx pod in a Kubernetes cluster. In this federated learning demonstration, we consider proactive measures to improve the performance of virtual reality streaming services by taking into account radio network conditions and application traffic. Each site has a radio access network that includes a base station and virtual reality streaming server and corresponding users. MonB5G components, namely monitoring system, analytics engine, decision engine, and actuator, are deployed near the virtual reality stream server to predict CPU utilization. Federated learning training sequence includes the interactions between the administrator, the aggregation server, and analytics engines. The visualization platform for federated learning training process includes components from the Elasticsearch stack. 3 containers are now up and running: Elasticsearch, Logstash, and Kibana pods. Visualization dashboard is also running. The aggregation server container has started and is now running and listening. Analytic Engine Site 1 has now launched. At Aggregation Server, it is successfully registered. It is now running and listening. The same happens with Analytical Engine Site 2. federated learning process has now started by the administrator. Normalized mean squared error and observed computation time versus federated learning rounds can be observed in real time. Both values converge at the end of the federated learning process. The metrics of virtual reality streaming video application and how MonB5G forecasting features can adapt are demonstrated here. On the top side of the figure, we can see the metrics for the Kubernetes-only solution. On the bottom side, we can see the metrics for the MonB5G solution when the number of virtual reality streaming clients is 6 in both cases. In Kubernetes-only solution, reactive scale-up is not enough to keep the videos playing since the pod is limited to a CPU usage that cannot support 6 virtual reality streaming clients simultaneously. However, with MonB5G forecasting, it will trigger scaling up action through the Kubernetes API when detecting that CPU usage is about to exceed the pod's limit. Long short-term memory-based anomaly detection solution provides early detection for unusual traffic changes, such as a sudden increase or a sudden drop in typical user traffic for a given time of the day. Early detection of unusual activity provides extra time for network adaptation or troubleshooting. Multivariate anomaly detection is implemented using Docker containers. The model is trained via normal instances across multiple variables. The trained model is used to detect anomalies in unseen test samples. 3 variables, namely CPU, outbound pod traffic, and average bit rate at G node B, are being observed. An anomaly detection is caused by the activation of 8 users at a period when only 1 user was expected, resulting in anomalies in the 3 observed variables. MonB5G demonstrated 2 solutions for zero-touch multi-domain service management. Federated learning-based resource predictor improves virtual reality streaming user experience. Anomaly detection provides extra time for network adaptation or troubleshooting.